but there are still a few features that stand out when you look at them directly. Now, if you try to look at a few more, you will see a few examples where things start going a bit wrong. You know, if you see sort of detached heads or eyeless cats, and you know, a child that has never seen a cat may start believing that, oh, actually, that's what really cats look like. It's okay for them to have detached heads. It's okay for them to have missing eyes, and that is absolutely normal. So the question really arises, well, is this real? Would a child actually be able to learn on this kind of data? Or would they start having some sort of misconceptions about what is real and what isn't? And also, there are some questionable examples here as well. So is the cat on the right, is it actually real? Well, you will not observe many cats in practice sort of ripping through a wall. And so the question of what is real, what is useful, what kind of information we're actually able to get out of the data, these are not sort of simple or direct questions we can easily answer. But we see that when training on generated data, something must go wrong, because if your model is even slightly wrong, then the subsequent generation will start thinking about what is real in a wrong way. And so to basically, the main question that I think many of us are asking is, can we learn from synthetic images? Are they actually useful? And the answer is we can. Sometimes we can, because obviously there is still some useful information in the images that we observe. But can there be issues? The answer is yes. And in this particular example, you will see sort of in the bottom right corner, you will see a watermark. And watermarks appear quite often in images on the internet nowadays. But obviously, this model learned to actually consider them as a part of a cat. Whenever you see an image of a cat, you should see a watermark. And that is definitely not real data. So there will be issues. And what we show in our paper, that it actually causes model collapse. It leads to inevitable worsening of your models. And over time, it can lead to really significant degradation. Just to give a definition of what model collapse is, we refer to it as a degenerative process, which effectively affects generations of learned models, because the data generated by the previous models begins polluting the training set of next generation models. So to give another example, you could consider GPT-2, GPT-3. Oftentimes, they get pre-trained on the whole internet. However, nowadays, your current content on the internet is mostly generated by GPT. And so you can imagine that this being an example. The problem of which we refer to in model collapse is that in the early model collapse, the model begins losing information about the tails of the distributions. These can be some sort of minority classes or minority features. Yeah, and then in the late model collapse, you start getting significant degradation, where you get a setting in which the model starts sort of entangling the different modes. It starts forgetting about big chunks of your original distribution. Oftentimes, you converge to something practically nonsensical. So to give you a visualization of the process that I'm talking about here. So first, we begin with some sort of original data, which we refer to as real data. We use that data to train our model, which then gets sampled. And those samples ultimately make their way into the next generation's training. So here we also assume that some amount of real data still continues on as being part of the subsequent training data, but the bigger chunk is still model generated. And then you can imagine that happening for n steps, right? And the reason why we will have errors is because we have, over these steps, three main errors getting accumulated. And those are effectively imperfect model architectures, because our models aren't extremely, our models are getting more and more expressive, but this comes at a cost of getting more and more parameters. Now, normally, to train very, very large models, of course, you need to go to very large companies to be able to do that. So oftentimes you still represent your models with some sort of limited architectures, and that inevitably leads to errors. But at the same time, we're also not extremely, we don't ever converge fully to some extent to a global minima during optimization procedures. So our learning also inherits a lot of biases, and these biases get propagated over time. And obviously, we have finite data, and I think this is the largest source of error, because 60,000 MNIST images, while that may sound like a lot, if you consider the dimension of the MNIST image itself, well, it is going to be, in the simplest example, is going to be 28 by 28, which is going to be 500. So 500 dimensions, but only 60,000 samples. We know that classically we should be sampling exponentially more with the number of dimensions, and 2 to the power of 500 is going to be much, much larger than 60,000. So we will obviously have a very finite, usually somewhat small number of samples, and these errors will propagate as a result. Just to give you a sort of a very, very toy example here, imagine you have two different real distributions, but you do not sample them enough. So you sample them for very, very small number of times. Then sort of in expectation, you don't really sample the tails. Your tails don't actually get represented. And so something that may look like real distribution 1 here and something that looks like real distribution 2, which are inherently very, very different, the model, after a single step, because of the sampling, it will not be able to distinguish them. And it will try to put the most simple model that it can. And effectively, this becomes this self-consuming loop where finite sampling leads to probable events being overestimated and then probable being underestimated. And we're only able to approximately fit. And so these probable events, they sort of overaccumulate, and your model starts becoming less and less varied in what it is able to produce. And so I will quickly mention this, because in the very, very simple Gaussian case that I think most people study when they're in school, if you fit an approximate mean and an approximate variance to your one-dimensional Gaussian, then it is actually, you can imagine sort of sampling it a very finite number of times, right? So if you sample the blue curve 3 times, and then you fit another one through those samples, you can see that you sort of start decreasing in variance, because if you were to sample the tails enough, then you would fit the true distribution much better. But this is very unlikely because they are tails. And so over time, if you repeat that for a few times, you will very quickly collapse to something with very low variance. And you can show mathematically what's going to happen. And the effective summarization of the slides is that you will collapse to something that looks like a delta function. And we are able to prove this, i.e. sort of a single sample with 0 variance. And what's more, you don't even know where that 0 variance sample is going to be. It can be anywhere. In expectation, it will go to infinity. And just to illustrate this, also in a slightly more complicated scenario, something called the Gaussian mixture model, where you have not a single Gaussian, but basically a bunch of them. If you were to repeat this fitting and sampling procedure for 200 times, 350, and 2000, you will slowly collapse to something with 0 variance. And but these have been very toy models so far. What happens when you actually go to deep learning? Well, deep learning is even noisier. It's even harder to make work. So here we consider the example of a variational autoencoder, which is another example of a generative model. And here is just the illustrative example. So the original model is able to capture what happens in your MNIST digits quite well. You can sample it and you have realistic looking images. But over time, and already by generation 20, these no longer look like real images. They start looking like some sort of average of a 0 and a 9, which I guess it believes to be the most likely sample. But over the generations, all of the modes just get entangled. You have only nonsense. Your tails get completely lost. It's only what's in the middle that is left. And the same thing happens when you consider large language models as well. So here are shown two graphs of perplexities. They might be a bit difficult to read, but the lower the perplexity, the higher the likelihood of the model. And so the higher the perplexity, then the more sort of not in tail distribution of the distribution the model produces the text. Effectively, what I'm trying to say here, it also occurs in large language models. But to give you an example that you can sort of connect with, if we asked the large language model to sort of finish this text, which talks about sort of architecture of parish churches in 1360s, your original model is able to sort of prolong the sentence quite a bit. But when you start sort of training with generated data, quite quickly you start spewing something technically real, but also nonsensical. And it starts by generations 5, it starts producing just a list of languages, and by generation 9, it just repeats black-tailed rabbits, white-tailed rabbits, blue-tailed rabbits. And the worrying thing is, this is not just an example out of context, right? This happens for every single example that we sort of posed for the model to continue. It would always start repeating almost the same nonsense over and over again. And the reason being is because it believes that content to be high probability. It starts forgetting about the tails of the distribution. And obviously, there are a few limitations specifically to how we have presented it so far, but just to say that this work has been picked up by a large number of people, and these examples have been extended to many, many different contexts, including diffusion models, including other generative models as well. They have been extended to large language models, since the experiments were not on the largest large language model. But the gist that I want you to take away from this is that model collapse is real, and we need to be cautious when training with artificial data. But so far, I've shown rather abstract, potentially examples. So I want to connect to something that may feel a bit more real for this particular audience, and here is a cut, is particularly on synthetic data in tomography. Tomography is something that I personally deal with quite a lot on a day-to-day basis, because it requires quite a bit of mathematics to actually get good tomography images. So here I would like to quickly recap what tomography is. And this is primarily work done by Max Kiss, who is a co-author of mine. Slides are based on his previous presentations, so thank you to him for that. So tomography, right? So what is the idea behind tomography? We want to be able to see inside certain materials or certain people, but we do not want to we want to have non-invasive ways to look inside of it. And the way that this particular imaging modality is performed is you have some sort of X-ray source that sends X-rays through your material, which in this case can consist of, I think, nuts and bolts, but normally you would try to use this in a medical setting that would be a human. And this results in 2D X-ray projections. And here, sort of on the right, you see an example of some sort of classical industrial tomography machine. However, when you send these X-rays, right, you don't directly get the image. Normally, what you get is a set of sort of 1D line projections, which we call a sinogram. No, so normally, as far as I understand, practitioners don't even get to see the projections or sinograms themselves. They usually see the resulting reconstructions. And here is shown as an example of a reconstructed slice in 2D. And so the problem that we, as mathematicians, quite often deal with is we are tasked with the process of, given those projections or a sinogram, how to reconstruct the actual image. And this is what we call the inverse problem. And oftentimes it is not well posed in the sense that the reconstruction isn't technically unique. It may not be sort of very stable. So small perturbations, small noise can lead to amplification of the noise. And the particular setting that is difficult is the super noisy setting, i.e. when we have very low dose computed tomography data. And here is just shown on the left an example of a very noisy reconstruction that we would get, which we would then try to somehow denoise. And this is the problem that we deal with, i.e. removal of artifacts and denoising in computed tomography reconstructions. And sort of more recently, a lot of deep learning has started finding its way to this particular area because, well, machine learning is quite good at dealing with image data. And for this reason, it seemed like a very natural extension to try to put deep learning for the questions of denoising. But then when it comes to deep learning, of course, we need a lot of data, but realistic experimental data is very rare. And sometimes it's not even about the rarity, but it's about the ability to actually use it. And in healthcare settings, to get real patient medical data, to then use it to train a neural network, that is a very, very difficult process, according to people in my group who have been dealing with that side. And so suddenly the question of synthetic data becomes a very important one. Can we use synthetic data to actually train to reconstruct? And so again, the problem that we deal with is we have high noise data that we're trying to denoise. Now, in order to actually compare this, we need real data. We need to compare the effect of synthetic data. We need something to compare it against. So we need real data. Now, this is where one of my co-authors went in and spent almost 2 years of his PhD collecting very many samples that he could then use to actually compare this. And here he acquired many samples with high, but also real noise, which he then spent a very long time sort of acquiring more and more and more data in order to reduce that noise. So in the end, we were left with high noise and low noise real data. And then you ask the question, okay, can we learn to denoise this based on synthetic noisy images? So in this case, the synthetic data that I'm talking about is simply synthetic noise. I'm not even talking about the data itself being real. And so this is the basic setup that I would like to tell you about, which is you have some sort of supervised learning paradigm where you learn to denoise computed tomography images. You have simulated noisy data and you have experimental noisy data, and as well as having experimental clean data. And then you ask the question, what would be better for us to learn on? Would it be better to learn on simulated data? Would it be better to learn on experimental noisy data? We know for sure which one is going to be less expensive because simulating noise is much easier than trying to implement it experimentally, because that is costly and in terms of both time and equipment. And as you can guess, the answer is experimental is significantly better. Now, this is a very large table. There's no point in sort of getting too much into the details. But the basic idea, so here on the left, it is the left side says which noise the network was trained on. and the right one says which noise it was deployed on. And the basic conclusion that I want you to take out of this table is that whenever you train on experimental noise, you do well on experimental noise. Whenever you train on experimental noise, you do well on artificial noise. However, when you train on artificial noise, you do not do well on experimental noise. And that is the worrying sign. So our artificial data, our synthetic data, is usually not up to par with what is happening in the real world. Our physics simulations, our best models for noise, are not good enough because they do not capture the actual difficulties, the actual inner workings of what happens in the real case scenario. So in this case, even when we try to remove as much synthetic parameters as we could, because we were still dealing with real data, just not real noise, we were already seeing degradation. And this is sort of the side of tomography that I wanted to talk about. Now I will also shortly talk about the fairness feedback loops as shown here, because in sort of in the first presentation that I talked about, in the first couple of slides, I mentioned that model collapse practically means that your tails get underrepresented. And this led to a very important question. Well, can we quantify this? Can we quantify how it is, how misrepresented the minority classes actually get, how they are affected? And so this led to a work from Ilya and his collaborators on directly trying to quantify this. And the setting in which they try to quantify this is a very, very manageable, but still a toy example. So in this case, they're able to actually directly quantify the property. So you can imagine a synthetic sorry. Um, sorry. So they decided to create a synthetic data set that on which you could directly quantify this. So imagine a setting where you have your images and you decided to color them one of two ways. You decided to color them either green or red. And then in your training data set, you decided to say, let me put a very small number of red digits, or for example, red nines. And then you could directly quantify what happens when these digits get, because obviously it becomes a minority class in this case, and you can directly track what happens to that specific class, sort of subset of your nines, and how it gets affected over time. And this can be done sort of in a number of different examples. And in particular, so the way that this is done in this paper is they, alongside training the generators, so these are the Gs, and those are the models that I used to refer in the first few slides. On top of those generators, you also have the corresponding classifiers. So you train a classifier on this generated data to distinguish between different classes. And you can all, as a result, you can sort of quantify the properties of this classification. So how misrepresented that data really becomes can be taken out as a property of the classifier. So we don't need to get too in depth into sort of the notations of what happens, but the point is that they're able to show empirically that your minority classes are the ones that get misrepresented the most. Effectively, they get disproportionately affected by by the virtue of information about them getting lost much, much quicker compared to the crux of the distribution, which is well represented. And now there are three graphs here, and there can be some ways to sort of try to mitigate this by oversampling directly the minority classes. But this tends to actually lead to even more degradation over time. But the gist of it is your minority classes get directly misrepresented more over the generations, and sort of, you know, after the gray area here, there's not much point in looking at the data because it practically becomes a random guess. And over time, at first we would see that there is bias towards the minority classes, but what is worse is that over time it leads to complete erasure. So your tails, as we have shown them on the graph of the histograms before, those tails get completely lost over the number of generations. Cool. And this can actually lead to something at first slightly counterintuitive, because if you actually look then at the performance of your models according to some standard metrics that you have, you would actually see that it would look quite good. The performance would not look necessarily that much worse. In fact, it would lead to some sort of the standard deviations on your errors would be much lower. But that practically happens because the information that you end up losing was in the tails. So now all of the generated data is very likely data. So you start losing your diversity very quickly. And the thing that I really want to get across in this talk is that you have to be very careful with your synthetic data because it can lead to unexpected behaviors. These biases are not just in you saying that, oh, I have nines that are red, nines that are green, and I may lose information about nines that are green. There are many features that may be present in your data which can be considered as minority features, and those can get lost very quickly. And whenever you would try to apply this to anything real, anything in a real setting, you will find that it would lead to a lot of degradation. And so what I want everyone to take out is be careful with synthetic data. And originally, when sort of creating this talk, I wanted to sort of create a nice overview of sort of where we started with this ideas of model collapse and sort of summarize everything that's happened. But it's I don't even think that an hour would be enough to go through everything that has happened. The work has been cited many, many times, and a lot of subsequent works has improved a lot on the kinds of models, the kind of settings that they consider, with the overall understanding being that model collapse happens. There is no obvious way of how to mitigate model collapse. There are some things that can be done, but ultimately, we don't know what to do. But I think this question might get answered in the future. But yeah. And I think this is everything on my side, and I fit into the 40 minutes.
Well, that's great. Thank you very much, Zach.